Now that we have explained the photovoltaic effect and semiconductors, let's look specifically at crystalline silicon, a semiconductor material used to make solar cells. We will explain how doping crystalline silicon can change the charge carrier concentration and how we can make a solar cell using the p-n junction. Crystalline silicon is the most commonly used material for solar cells. Silicon atoms each have 4 valence electrons, and when they are in a crystalline structure, they are each bonded to 4 neighboring atoms. A 2D model of the structure would look like this. Now here, it is hard to conduct electricity because the vast majority of these electrons are in these bonds, shown in red, at an energy state way lower than the conduction band. So what happens if we add an impurity to the silicon crystal? This is what we call doping the silicon. We can add impurities in 2 ways. Firstly, we could add a phosphorus atom in the mix. Phosphorus atoms have 5 valence electrons, so there will be an extra electron. This means that there will be another energy state close to the conduction band called a donor state. It is important to note that we aren't changing the charge of our material here. While we added an extra electron, we also added another proton into our material to even it out, changing the distribution of electron states by adding another higher energy state to our material. Electrons in these donor states are very close to the conduction band, so they can very easily jump to the conduction band and become mobile. We call this n-type doping because there is an extra negative free charge carrier in the mix. We could also do the opposite. We can add a boron atom, for example, which only has 3 valence electrons. This leaves a hole in our bonding diagram. This adds energy states close to the valence band called acceptor states. As these states are close to the valence band, valence electrons can easily jump to the acceptor state, leaving a mobile hole in the valence band. Just as with phosphorus doping, we are not adding any charge to the material, since boron compensates the lack of an electron with the lack of a proton as well. However, now we have an extra hole in the valence band, and holes in the valence band are also mobile charge carriers. So with this boron impurity, we have added a positive free charge carrier. We call this p-type doping. When we dope silicon with either boron or phosphorus, we use tiny concentrations. 1 impurity in a billion silicon atoms is enough to significantly alter the conductivity of a semiconductor. We can use p-type and n-type silicon to make electronic devices. If we place p-type silicon next to n-type silicon, we form what is called a p-n junction, or, as you may know from electronics, a diode. Free charge carriers from both materials diffuse to the other side. There, they will find an opposite charge carrier and recombine. Eventually, a steady state is formed, and we are left with 3 regions in the diode: the p-type and n-type regions, as well as the so-called depletion region, where charge carriers are depleted through this mechanism. This is what the band diagram of the p-n junction looks like. The p and n doping change the relative energy levels of the band diagrams of our material. So when they come together, the full diagram looks like this, with a curve in the depletion region. We can use this structure as a solar cell. Recall from the last video that we need to accomplish 3 steps to realize the photovoltaic effect: generation, separation, and collection of mobile charge carriers. Here is the band diagram again of a p-n junction. In a crystalline solar cell, one of your materials, the substrate, will be orders of magnitude thicker than the other. In this example, we have a solar cell with a p-type substrate, so we have a very thick p-type layer and a very thin n-type layer. Most of the generation step will happen in our thicker material, which, in this case, is our p-type substrate. So we'll focus there first. There will be many electrons at the top of our valence band and almost no electrons in the conduction band. When photons of sufficient energy are absorbed by our material, we will generate mobile electron-hole pairs. Next, the charges will begin to diffuse. Importantly, when there is a slope in the band diagram, electrons in the conduction band can only move downwards, and holes in the valence band can only move upwards. Therefore, as the charges diffuse, the electrons that reach the depletion region will move towards the n-type region, but the holes will stay in the p-type region. Eventually, charges will be effectively separated. This has an effect on the band diagram as the energy levels shift. If we show our metallic contacts, there is now a voltage difference between them. If they are connected to an external circuit, the electrons flow from the n-type region to the p-type region and recombine with holes on the other side. Therefore, the energy of the photons is converted into electrical work. If the cell is continuously illuminated, this process will continue, and the generated current is called the photocurrent. Here, we discussed three main topics. We explored the properties of crystalline silicon, which is the most commonly used material for solar cells. We discussed how doping can affect the properties of crystalline silicon. Finally, we showed how a p-n junction can be used to make a solar cell. Next, we will describe the p-n junction electrically using an IV curve.